calculating the change in concentration after a whole number of half-lives of a first-order reaction. So first-order reactions follow the same kind of kinetics as far as half-lives go as radioactive isotopes. So we can use the same approach when we're talking about the change in concentration of a reactant in a first-order reaction. So I like to use the ratio between, I'm using A for activity, but obviously that can be the concentration at time t, and A0 be the concentration at time 0. And N would be the number of half-lives that have elapsed. So to find out how many half-lives have elapsed, is it half-lives or half-lives? I feel like grammatically, because like a half-life is kind of a concept, it might be half-lives. Um, that's what I'm going to go with. I know it feels weird to say that, but I think that's technically correct. I'm overthinking things now. So if n's our number of half-lives, if we know how much time has elapsed and we know what the half-life is, then we can just take the total number of time and then divide it by the time that one half-life is to get up how many half-lives have elapsed. So given the information that we have here, that is exactly what we can do. So we can work out our number of half-lives is going to be the total amount of time elapsed, which was 64 minutes, divided by the time of one half-life, which is 32 minutes, and 64 divided by 32 is going to equal 2. So this is a pretty straightforward example. A lot of you guys might have already like worked that in your head about a minute ago, um but I'm trying to show you the method. Okay, so like perhaps there had been an uncountable number of half-lives, so just doing the counting half-lives is all very well and good if you've got like 2 half-lives, 4 half-lives that have elapsed. So if you've got 20,000, that's suddenly going to be a little bit harder to count. Okay, so we've worked out how many half-lives have elapsed. So what I'm going to want to solve for in this equation is AT, right? The concentration at the current time t. So I'm going to rearrange my equation so that AT is the subject. So A0, the initial concentration, times 0.5 to the power of n, which is our number of half-lives, whatever you like, that have elapsed. So then I can just plug and chug in there. And obviously whatever the units I have for my initial concentration are going to be the same units as what my final concentration comes out as, because the 0.5 to the power of an integer n is going to be unitless. So look for what units your answer is requested in, but if it's the same as the units you were given the initial concentration in, you can be a little bit lazy here as far as dimensional analysis goes. So 0.62 micrograms per milliliters was my initial concentration. Multiply that by 0.5 to the power of 2, which is the number of half-lives that have elapsed. And that will give me 0.155 micrograms per milliliter. So that is how much my concentration has decreased to. And I suppose I should probably give that to 2 significant digits, so that'd be 0.16 micrograms per milliliter. Okay, so hopefully that is a useful approach for this kind of problem.